Hi everyone. I'm Raymond Clay. I'm from Sandia, and I'm going to be filling you in on our attempt to do analytic gradients in QMCPACK, particularly focusing on forces. So just to sort of give an overview of my talk, here's sort of where we are and where we're going as far as forces go. So we've been targeting non-local pseudopotential calculations, and so far we have a working implementation. I'm putting an asterisk here for both open and periodic boundary conditions within VMC. And what's the asterisk for? The underlying functions needed to compute all the analytic derivatives and stuff are in QMCPACK. They're unit tested. There's some tweaks you as a user might have to do to get it working, but if you're interested, talk to me. I want to stress that this primarily works with VMC at the moment, and I'll go into the technical reasons for why that is soon. We are focusing on Slater-Jastrow type wave functions, so single determinate with 1 and 2 body Jastrows. We support both the Ein-spline and the localized or LCAO type basis functions, either in periodic or open boundary conditions. And currently, we're sort of focusing on making sure that the formalism is correct. So we just did a very naive implementation for all these derivatives, and currently it scales like into the 4th a number of electrons. So what we're doing at the moment is we are trying to extend, or we're basically trying to test and validate everything up here, sort of moving towards doing these forces in DMC. I'll go into the technical reasons for why that's not done yet in this presentation. Moreover, we'd like to do sort of fast derivative calculations. We want to bring the scaling down from n to the 4th to n cubed. So there are methods in the literature where you can actually compute all the force derivatives for only like a factor of 3 or 4 more than an energy evaluation. We also want user friendliness. As I said, there's maybe 1 or 2 lines that you need to uncomment in the source code to be able to start playing. That's not very user friendly. And lastly, what we'd like to do is we'd like to move and support more wave functions. 3-body Jastrows in particular, I think those have been demonstrated to really improve the locality approximation, and they're just a good all-around good idea. But moreover, we'd also like to support multi-determinate wave functions. So why is this hard? Well, we've sort of taken the approach of, in the literature known as the Zero-Variance, Zero-Bias Estimator framework. This was pioneered by Asaraf and Caffarel back in, there's a year here, probably 2003 or something. But the idea is that, if you go into a DFT code, they'll often invoke the they'll use the Hellman-Feynman theorem, which basically means that, when you start taking a derivative of your total energy, you'll start having these, actually a fair number of terms that pop out, but if you're at a variational minimum, you can actually ignore most of these things, so that the force estimator is really just a derivative of your Hamiltonian. So where do all these other terms come from? What's their use? Well, in QMC, if you look at the expectation value for the energy in VMC or DMC, and you just take a straightforward derivative, this is actually the full expression you come up with. Now in VMC, this term is going to be 0, so why do we include it? Well, if you look at these 2 terms here, what this is literally is a derivative of the local energy. So in contrast to the Hellman-Feynman estimate, we basically, as we improve the quality of our trial wave function, the fluctuations in the local energy decrease. It approaches the correct energy, and as such, we get we sort of inherit that property for the derivatives of the trial wave function. And so as we approach the exact, so as the trial wave function approaches the exact wave function, as its derivative approaches the exact, we basically have a zero-variance, zero-bias force estimate. So basically, this is the zero-variance term over here. It sort of, this is where it comes from. And this term is a zero-bias term. You can also convince yourself that this term also goes to 0 as you approach the exact wave function. So in practice, we're not going to have the exact wave function, but it's still desirable because it still represents a variance reduction. And the lower the variance, the less computational time we have to spend in order to be able to get a useful force estimate. So we have really been focusing on pseudopotentials. That's because, once you clear the first row, it's pretty much insane to do all electron calculations. And most of the systems of interest, like transition metal oxides and stuff, we have to use non-local pseudopotentials. So what we've done so far is, just focusing on the Hellman-Feynman term, that's this guy up here, is we've implemented procedures to calculate explicit analytic derivatives for this, the local piece of the non-local pseudopotential and the non-local piece, both in open and periodic boundary conditions. The big caveat I would say is that we basically take the derivatives within the locality approximation. We are not taking derivatives of the T-move sort of components yet, but in the future we'll certainly do that. So we've done some pretty extensive validation of this in both open and periodic boundary conditions. Here's a snapshot of a fun little table from 8 sodium atoms in a box, and we basically just compared the QMC numbers without a Jastrow to the Hartree-Fock numbers. This number over here is the difference between these two, and this is the Z, sort of the how many standard deviations it is off of the QMC estimate. And you see everything's within 3 sigma. So, and this is like well below sub-millihartree accuracy. So in periodic boundary conditions, we agree with other electronic structure codes. In open boundary conditions, we've done the same thing, and it looks pretty good. So at least that term is done. Most recently, we have been going through the code and have been trying to implement the so-called zero-variance and the zero-bias terms. And basically what we need in order to be able to pull this off are these following terms here. Most of the complexity comes from the Hamiltonian acting on the derivatives of the trial wave function. Fortunately, we have implemented the sort of kinetic energy contribution to local energy, the non-local pseudopotential contribution to the local energy, and just our usual analytic derivatives over here. So we can support Slater-Jastrow wave functions, 1 and 2 body terms. And as I said in the beginning of the talk, we can do ion-splines or LCAOs. Provided there's no, with ion-splines, there's no explicit dependence on the ion coordinates, so this is trivial, but this term also works. It's been validated against finite differences and whatnot. As I said, currently this is sort of the reference implementation. It is very slow. Like, this is probably not going to be able to hit large system sizes, but at least for molecules and small unit cells, we can use it. And more importantly, it's important to sort of set a benchmark for ourselves and be able to tell if the formalism is right. So what I'm going to do first of all is I'm going to show the tests we've done on the zero variance and zero bias terms for a nodeless system. And the reason I'm using a system without any nodes is for technical reasons. There are some divergence issues, which I'll talk about very soon. But what I'm going to do is I'm going to consider a sodium dimer in periodic boundary conditions. I'm going to use a VFD pseudopotential. It's got 1 electron in the valence, and so it's a singlet wave function. There are no nodes in this system. I just put in a cubic box, and again used, since this is a bosonic wave function, I actually don't have to use single particle orbitals. So I used a 1 and 2 body Jastrow wave function. I optimized it, basically 6 Bohr, and froze all the parameters. And so just to set up a reference, what I did was I just pulled the dimer apart, computed the VMC energy here, and fit it to a 5th degree polynomial. And then here's the results. What I'm showing you here is the force computed a whole bunch of different ways. This DDR-EL is the derivative of the fit I made to the local energy, so this is my reference point. This HF is the Hellman-Feynman term. We see it in red. The ZV term over here, this is kind of nice because when you add it onto the Hellman-Feynman term, it doesn't change the answer. It is rigorously 0 as it should be. The main difference is that the error bar is a factor of 2 to 3 smaller than what the Hellman-Feynman term alone would have had. When we include the zero bias contribution, we bring this thing right back onto the reference implementation. So that's pretty good. And so basically to conclude with this bit, we find that our analytic forces evaluated in the VMC sort of Nodeless case agrees with the direct differentiation of local energy within error bars. And there are terms that are actually important. For instance, if we did not include the zero bias term, we would be off by 1, 2, 3 millihartries per Bohr in this test case. Cool. So why did I test a nodeless wave function? Well, it's because if we look at the let me take a step back. Basically, with a naive implementation, the estimators, or that estimator I wrote down at the beginning of this presentation, actually has infinite variance when you have nodes. And the reason for that is basically because of this term right here. Now, the local energy, for instance, also has a trial wave function in the denominator, but you can sort of convince yourself that, or basically, local energy is marginally stable, or it has a marginally finite variance. One more factor of a nodal divergence in that denominator and sort of ruins everyone's day. So we basically need to deal with the fact that, so basically we have to figure out how to deal with that. And unfortunately, we can do this, we can solve this quite elegantly using a guiding function. So let's just take an arbitrary observable in VMC. Here's our Monte Carlo estimate. Well, if I multiply and divide by a guiding function, which I'm going to call psi g, then I can, just use a basic mathematical identity to show you like these two are going to be equivalent, except as long as I take into account like weighting factors. And the key here is that while the local energy and while the force, the zero-variance, zero-bias forces diverge as you approach a nodal surface, that 1 over d squared divergence is going to be canceled out by this term over here, which goes to 0 as you approach a node like d squared. So that's super nice. Okay, so what we've done is that the guiding function that's been used in the literature basically measures the distance from the node according to a Frobenius norm of the matrix Slater determinant inverse. And so what we do is we take this really cryptic-looking guiding function, like I said, straight out of the literature. In this case, we're going to test out a carbon dimer, mainly because it's got 4 electrons per carbon atom. It's definitely got nodes in it. And, it's a fun little dimer. So we basically use Slater-Jastrow 1 and 2 body terms, LCA orbitals from Hartree-Fock. I believe these were taken from quantum package. And for this test case, I'm going to set epsilon equal to 1 times 10 to the minus 4. And what we see is that I'm showing 2 traces of one particular force estimate on one of my carbon atoms. I think it's the X component just along the dimer. And we see that without a guide, most of the estimates are clumped up here, but we have these spikes. And more troublingly, we have pretty large spikes. And sometimes you have to run a while, but like invariably you're going to have these. It's going to like trash the variance estimate. But if you put the guiding function on, you see that we still have these little fluctuations, but you can run it out for 30, 40,000 steps and not see anything like this. So that's super nice. So doing the exact same thing I did with the sodium dimer. I apologize for the curve. The sign convention is different, but it's basically looking at I believe in this case, positive means that the force is sort of pushing the dimer apart. Negative means it's attractive. So Hellman-Feynman term. That's over here. We see the zero-variance term is right on top of it, as it should be. And then what we show is the Hellman-Feynman plus zero-variance, zero-bias corrections over here. And notice that these things sit right on top of the VMC, the differentiated form of the VMC local energy, which is nice. That's what it should be doing. Now, what I'm going to do is I'm going to zoom in a lot. Like, we're going to look at the error scale on this axis. So, 0.8 Hartrees per Bohr at the most compressed. Now, in order to be able to even start to see a difference between the fit and the force estimates, we have to go to this scale over here. And even so, the difference between the finite difference and the zero variance, zero bias estimators is within statistical error bars. So, and like I said, this is 1 millihartree per bore, and I still can't really see a difference. So, moreover, in this particular case, we're still seeing a consistent 2 to 3-fold reduction in the error bar, which means a factor of 4 to 9 improvement in the variance and therefore computational efficiency. So I would say this is pretty well validated. This looks pretty good. So where are we going next? Ideally, we would like to do this with DMC. And so the main problem there is that, well, there's 2 main problems. One is that we have not implemented a guiding function yet. But here's sort of what we need to implement. These terms are identical to what we had in the VMC case. This term you'll recognize from the VMC case. The main difference is this guy over here. So there are multiple ways to do this to varying levels of rigor. One of the most common things people do is just replace this with the trial wave function. And as you approach the exact trial wave function, this term goes to 0, but you do incur an error. We're looking into ways to do forward walking and stuff to make this rigorous. And as I said before, the other thing we need to implement is a guiding function. Fortunately, I'll talk about that in a second. So let's just jump back to the sodium dimer in this case. This is the same test case I showed you at the beginning of the talk. There's no node, so there's no nodal divergence. What I'm showing you here is the Hellman-Feynman term. In this case, the zero variance term is not really required to be 0 anymore. So we see it bounce up, but if you include all the terms, that brings this term down to, this is the total force estimator using this approximation that, the fixed node wave function is about equal to the trial wave function. And this is the finite difference of the DMC energy. And you can see that there is a measurable bias, but it does improve the results quite significantly over the bare Hellman-Feynman. And this can definitely be improved by either optimizing the wave function out here or improving the quality of the trial wave function. So, if you're in a pinch, you could probably use this. Depends on how bad the DFT forces are and whatnot. So the thing seems to be stable, seems to work in the Nodeless case. What we need to do is we need to sort of implement the same guiding functions we did for VMC in DMC. Unfortunately, it's the exact same trick. It's the exact same. We need to compute the exact same things. The main thing holding us back is we need this object now instead of just the ratios. So I'm working on that frantically. So hopefully that should be done reasonably soonish. So using these forces, there's not very many free parameters as a user that you'll have access to. Basically, when everything's online, you just need to go in and add a term like this. I believe that in the main code right now, you can actually access a lot of this functionality. It might crash. It's a research code, so like I said, talk to me afterwards if you're interested. But you just need to tell it that I want to compute a force. I want to use this particular type of force estimator. This is short for Asaraf-Caffarel force, and then it should just go to the races. To handle the guiding functions, you basically have to go into the QMC driver itself. So if you're running DMC or VMC, you'll add this extra line into the XML block. And this basically tells it to use a guiding function instead of the trial wave function. There might be one more parameter so that you can sort of tune that epsilon. But as I said, it's once it's implemented, it'll be very easy for a user. It's just not quite 100% there yet.
Right?
Yes.
Sorry, I have a question.
Yes.
So I understand that it's super useful to have the forces, but my guess is that you're not going to get geometry. And basically, however, to go from having from going from forces to optimize geometry requires doing a back and forth with software to generate new orbitals according to the new forces that you
get.
How close, or is that something provided? Is this something where once you compute the forces, you also can dump these are the coordinates that you should run if you wanted to have better geometry.
So I think that in the short run, I think geometry optimization and actually using these things should probably be handled on the Nexus side.
Yeah, but I mean, is this something that is possible? Like just plainly, like you have the force. Can you, from the force that you have, derive new geometry?
Yes, it would be one step of, Newton method or yeah.
Just add lambda times the force and off you go.
Yeah, exactly. So,
but that's not provided yet?
Well, that's maybe one line.
But as I said, that's a prime use case for Nexus in this case, because basically the geometry optimization algorithms themselves are not that crazy. The dominant step is going to be in
Of course, this is why I'm asking if just that last step is there, that we can still start using it.
Oh yeah. No, that step is not there, but we should talk about it afterwards.
One point that you have to really be able to variable functions.
Yes. Yeah. So.
To do outside.
Yeah. So that is that's sort of why I'm recommending. Nexus is probably the easiest way to go about it. I think you can integrate the codes way more tightly. I mean, like PySCF, or there are ways to build Quantum Espresso as a library, so you could at least short circuit that entire diversion into I/O. But yeah. So anyways, so that's sort of the status. So we've been working on like I said, a PR or two more, and the DMC forces should be pretty usable. We really want DMC forces though, because that's sort of where our spectacular accuracy comes from, is from the projection step. So we want the forces to be as accurate as that. Moreover, we are definitely interested in moving in the direction of trying to improve the scaling of these things so that we can do large-scale calculations. And yeah, I think that's probably that's all I got. If any of you are interested sort of in the formalism, where all this stuff is coming from, or what we're implementing, these are the main references. Everything 1 through 4 up here are all just general QMC, general problems of guiding functions and how to do things fast. And then if you want to get down to the weeds of what's implemented, you're taking derivatives and pseudopotentials and T-moves, this guy's a nice place to start. So with that, I think I'll take questions or comments or criticisms if they're not too harsh.
Right, questions for Ray?
Yes.
The slide of the PDC, the boundary conditions, I didn't understand why it's so different than the other cases. Is it because of the boundary conditions?
No, it's a sign convention.
Sign convention.
Which direction do you take as positive and negative? So, and I was doing it here because it's I thought more about this figure and thought that positive would mean repulsive, but just flip it.
No, but I mean, why the Hellman-Feynman is so deriving the energies?
Oh, so what?
It's different than the corrections. The last one. No. So here, for example, here you have
the DFT estimator that it doesn't sit exactly on the numerical derivative.
Here, the red triangles and the green can be very well.
Yeah.
And not in the PVC case.
So the reason. Dang, why is it so slow? Was this case you're talking about, or?
No.
DMC.
DMC. Yes. Okay. This guy.
Yeah.
Well, so the reason that they don't agree, basically this case is one not on a variational minimum, and there are Poulet terms in this. This is an LCO basis set. There are contributions. Yeah, but it's actually, there's contributions from both.
It's a little bit deeper problem, because here you have, this is the operator which doesn't commute with the, therefore error is of the first order.
Yeah.
And what you see is how big that first order term actually. So you need to include that into the trial function explicitly in order to cancel it out.
Yeah. So is it too hard to implement things so we can choose the atoms where we want to evaluate the force? Would that save computer time or?
I don't, I think it would, well, it absolutely would save some time. I don't. So.
I'm going to jump with the questions. So if I was paying sufficient attention, just about got DMC forces, single determinant wave functions, and 1 and 2 body.
Yep.
And both splines and Gaussian.
Yep.
Okay, so right, that's a huge improvement from big step 1. If someone wanted to do like DMC is where we get a lot of our accuracy, but already in VMC we've got no self-interaction, there's some sensible van der Waals and so on. So there are some systems, some molecular systems, where that's probably quite good, even single determinant, if 3 bodies there.
Yeah. So I don't have the presentation here, but anyone interested, I can show the exact functions that need to be implemented. Basically, you need to override 2 functions in the Jastrow to be able to have this capability. So, and in that function, you would need the analytic derivative of whatever Jastrow object you're doing. So
yeah, so it's just DJ3 by dr times of, essentially.
Yeah.
Darren had his hand up.
Right, so this is thinking a little further in the future, but force derivatives in periodic boundary conditions, they're taking the derivative of the energy where you've got inward sums for the potential.
Yes.
If you're doing something like a cold curve, even equation of state, you need finite size corrections to get the total energy curve to be correct.
Yeah.
Has there been any thought in the literature or elsewhere about what you need to get forces corrected for finite size effects in periodic boundary conditions?
So I believe that if you looked at all right, so I know for all electron, you can also write the Hellman-Feynman force as an integral over basically 1 over r squared, the electron density. So the question is, how fast does the electron density itself converge as the system size increases, I think. I think that's the dominant effect here. These are nice little rigorous things to drop the variance and bias mainly from the non-local pseudopotential piece, but that's, if you hold a gun to my head, that's what I think.
Okay, maybe a hard question. So this discrepancy, one would think that this is really caused by a static nodes in the problem.
A discrepancy on the DMC side?
Yeah, on the DMC side. And so maybe there might be a way how to wiggle it a little bit and get it off.
I'm still kind of puzzled. It seems to me, just like people learned over the decades, is that you have to take derivatives of everything.
Yeah.
And you can't just hope that something isn't important. So because it always ends up being important. So, it's not clear to me, are you taking derivatives of the trial function?
So it's a lot easier to see with the DMC expression because I kept some terms, but this is for VMC and DMC. This is literally what I'm taking the derivative of, and these are the terms that come out from the numerator and denominator of your local energy expectation value over your.
It seems like, if it's done properly, it seems like maybe you have noise, but it should still be averaging around the right curve. I don't understand where this shift comes from. Result,
So let me.
You have a very smooth curve out. It's just wrong.
Yes. Well, so in this particular case, anyways, so I know that this term over here has to, this. Let me see here. So in VMC, I know for sure that this term over here has to go to 0 because you can take the Hamiltonian, operate to the left, and basically get the local energy that way. But in this particular case, I don't think, I'm not sure if that's going to work the same way in DMC. So.
All right, last question.
It doesn't commute. another term. So we'll have a first order error in there. It will not be second order like it's total.
Yeah, but it's not like it's not a stochastic error. It's like a bias in the result.
Right.
I mean, it's not just from random
No.
fluctuations.
It's a real bias.
Yeah, so,
I think that's related to my question. So the force operator doesn't
Yep.
commute with the Hamiltonian.
Yep.
Which means that the asking for the force in the ground state is just the mean value.
yes,
And they will have quantum fluctuations in the force itself.
Yep.
So those two terms that you have to write that are not naive at all, would they help you to actually estimate the fluctuations of force? Or you have to do a completely different calculation? Because it seems that some information is there
yeah,
of the fluctuations of the force, and you could use the fluctuations of force for other physics.
yeah.
It's important.
That is, I will have to think about that. Yeah, that is super interesting. So,
For example, the other processes I have are usually time-dependent DFT. One important one is the quantum friction that comes from electrons.
yeah,
The fluctuation dissipation theorem, both are related.
yeah,
And so in some sense, you have the fluctuations of the fields. But you have a friction term
yeah.
here for moving ions.
Okay. Yeah, that is super interesting. I will think about it. Yeah, thank you.
All right, we should move on. So thanks so much, Ray.